So in this assignment, you are going to calculate the viscosity of liquids that have these compositions here that I'll be giving you in a spreadsheet that are from the chaos crags of the Lassen Volcanic Center as analyzed by Michael Klin. And in this very first entry, I show a composition from a paper by Giordano et al. Published in 2011. I'm entering this value here because we want to make sure that we enter their equations for calculating viscosity correctly. They give a sample calculation, so it's very important for us to put in their sample liquid composition, which we will do so here, and then we can check to see that we can reproduce their numbers. Well, the first thing we need to do is take a look at their table 1. So we'll move on over here. Table 1 has a series of coefficients and variables. So the coefficients are these B values here, and the variables are the oxides. All of these oxides are expressed as mole percent, as they indicate here. So the very first thing you're going to have to do, I'm only going to give you information out to column Q. Everything else is going to be up to you to input. So the first thing you'll have to do is calculate liquid compositions as mole proportions, where you will take, let's say, the silica content that's mole proportion will be the weight percent that will be given divided by its molecular weight, and you'll do that for each of the oxides here. You'll get an odd total. They want mole percents. So in the next set of columns, for me, it's columns I through AT. We renormalize those values so that they equal 100. So we take 100 times silica, the silica mole proportion, and divide it by the total for the renormalization. Here I've got a total, and I added up just to check that it works out to equal 100. They're going to use temperature as an input, and they want temperature as kelvins way over here. Sorry for going back and forth so quickly. We've got temperature inputs. We'll just assume 1,000 degrees for now, and then we don't really need the pressures here. We'll use them in a later calculation for density, but we've got pressure input as kilobars and gigapascals. All right, let's look at the calculations. So once you have your mole percent values, if you take a look at the equations here, these are equations from the papers. You can look in Giordano et al. To see that I've reproduced these correctly. The log viscosity is what is calculated in this expression here, where it's equal to A. A is just a constant. He gives it to, or she gives it to you here, minus 4.55. And then we're going to add to that B divided by temperature minus C. The B and C are the things that we have to calculate that depend on the composition. Let's see if we can recreate the value B. I've done so over here and here. What we're going to do is try to reproduce the values for B. And I see that I've got a component missing, so we'll fix that. All right, so for B, how do we calculate this? All right, so we'll calculate it from scratch. And so for B, we have I goes from 1 to 7, and the B sub I, notice there's B that goes from 1 to 7, and we have all these 7 values here. So for B is equal to 1, then we have 159.6, and that's going to be multiplied by M for that same case of I is equal to 1, and that's silica plus titanium. I've already taken the sum of silicon titanium here, so I don't have to go back and take the sum over there. It just makes it a little bit easier to follow these equations. We need to subtract from that minus 173. So this is for B2, 173.3. That's being multiplied just by aluminum. So we'll just grab that mole percent there. And what's next on the list? We are going to add to that 72.1. That is for the case of B sub 3. So the mole, that's B sub 3 is 72.1, and the corresponding mole fraction is iron, manganese, and phosphorus. I've already collected those, so I'll just take that sum there. Then we're going to add 75.7. That's our B sub 4, and it's going to be multiplied by magnesium. And then we're going to add to that, or rather subtract, 39 multiplied by calcium. And then for the next entry, we have minus 84.1. multiplied by sodium plus V. V is vapor, and I already have that sum here. And the vapor is really just the water content, so it's this guy here. I've just taken, in this column here, I've taken the sum of sodium plus vapor, so you can see the 3 plus 6, etc. gives us something a little over 10 when you add the decimal places. And then where are we at? We've taken care of the B sub 6. We want to finish this off with the B sub 7, which is plus 141.5 multiplied by vapor, which again, I think it's V for vapor, but it's really just the water content, plus the natural log of 1 plus H2O, and we've got that value here. Now we have to start adding these fellows here. This is the Bij, which are the 1, 1, 1, 2, 1, 3, and so we'll continue the sum. I don't know if they really needed a separate set of coefficients out here, so we're going to take minus, I put a plus, we need minus 2.43, and that's being multiplied by the product silica plus titanium, which is this guy here, multiplied by Fm, which we have here. And I've already created that cell to make it a little bit easier. And then the next value is a minus 0.91, and that is being multiplied by silica plus titanium plus phosphorus, multiplied by all that other stuff. I've segregated that out over here, just a little bit easier to do it in bits and pieces. And then we have a plus 17.6, and that is the B13. So it's the last part of these, and it is being multiplied by aluminum times Nk. And I've already got that there entered. And that's the end of the B part of the equation. We'll hit return 7730. I have reproduced what I've entered earlier. So C works the same way, except you're now going to work through this column creating sums, and you should get a value of 335. Or should we? Well, the neat thing about table 2 is that if we enter the composition here, which we have, then for this water content and for a temperature of 1273, which is the temperature we're using over here, then we should get A, B, and C values and a total viscosity that are indicated here. So their A value is a constant. Their B value is 7720. I get 7730. Their C is 334. I get 335. Probably the difference there is I did a lot of rounding when I calculated the mole proportions. And then for the log viscosity, I'm simply entering this equation. So it's minus 4.55 plus the B divided by the temperature, A minus C. And I'm grabbing that temperature A, that is in kelvins. And then for the total viscosity, we'll just raise that log viscosity to the power of 10. So I've gone through this very quickly. I want you to try to reproduce these values from Giordano et al. Using these equations, and then go ahead and fill down. Be careful when you fill down to keep all the cell references that are constant, that they're truly constant, and calculate the viscosity for the volcanic rocks that have been erupted in the chaos crags in the Lassen Volcanic Center.